Hi, my name is Guy Boyde. I've just started a one-year postdoc at the University of Southampton in the UK, mentored by Ian Leary. And until about a month ago, I was a grad student also at Southampton, and my PhD supervisor was Stephen Terrio. And I'm looking for jobs starting in autumn 2022. In the broader sense, the work I want to tell you about concerns the asymptotics of homotopy groups. And throughout this talk, homotopy groups are going to be unstable. Like it or not, we're in the following situation. There is no simply connected CW complex, all of whose homotopy groups are known, apart from contractible examples, right? And this doesn't look like changing anytime soon. So one response to this situation is to look for weaker questions, questions you might actually be able to answer, but which nonetheless say something about all homotopy groups of your space simultaneously, right? All pi n. And the question I want to ask is, fix X, what happens to pi n as n goes to infinity? Now, the first thing to know about homotopy groups is that they're always finitely generated abelian, at least when the space is simply connected. And this goes back to Serre. So for such spaces, and we're going to be simply connected going forward, each pi n is a finite direct sum of, well, two kinds of thing, right? On the one hand, you have copies of Z, the infinite cyclic group, and on the other hand, you have copies of Z mod p to the r. So some finite cyclic group whose order is a prime power. If you ask about the number of Z summands, that is to say the rank of these groups, then that's the part of the problem that rational homotopy theory sees. And on that side, really deep and powerful results are known. And I want to tell you about this theorem because I think it's really nice. So take such a space. One of two things can happen in its homotopy groups. And on the one hand, the rank of the direct sum of all of the homotopy groups could be finite, right? So you look across all the homotopy groups and you only see finitely many Z summands. Or the alternative is that the rank of the partial sum of the first k homotopy groups grows exponentially with k. So this dichotomy eliminates a bunch of stuff in the middle, which a priori might have happened. Namely, there's no such space where the rank of this partial sum grows, say, quadratically with k, right? And from this dichotomy, we get some terminology. So the spaces where there are only finitely many Z summands in their homotopy groups are called rationally elliptic, and the spaces where the number of Z summands grows exponentially are called rationally hyperbolic. So in a paper that went up on the archive in 2017, Huang and Wu, for the first time, begin to import this kind of thinking into the study of the torsion bits of the homotopy groups. So their definitions go as follows. You fix a space X and a prime P, and you look at the partial sum of the first k homotopy groups. And this thing is finitely generated abelian, so it decomposes. And in there, you can count the number of summands isomorphic to one of Z mod p squared, Z mod p cubed, and so on. So the number of cyclic groups whose order is some power of p. Now, if this number grows exponentially with k, then I'll say that my space is p hyperbolic. But I could also ask a finer question. I could only count summands of some particular power of p, right? So I can fix r, and then if the number of cyclic groups of order p to the r grows exponentially with k, then I'll say that x is z mod p to the r hyperbolic. So in particular, z mod p to the r hyperbolicity implies p hyperbolicity. Here are some examples. So the first thing you should think of is the wedge of two spheres. If I take two spheres and neither of them is a circle, then this wedge is whichever prime I picked and whatever power I raised it to is going to be z mod p to the r hyperbolic. So I see exponentially many copies of z mod p to the r appearing as summands in its homotopy groups. How does one show this? Well, for those in the know, the two ingredients you need are the Hilton-Milner theorem and the J homomorphism. And those are basically the two pieces. The second main example is a Moore space. So if the parameter I put into my Moore space is a prime power, and the Moore space is simply connected, then writing p to the r for that prime power, I get z mod p hyperbolicity, z mod p squared hyperbolicity, and so on up to z mod p to the r, and finally z mod p to the r plus 1 hyperbolicity. And in the case where the prime p is at least 5, this is a complete answer. Because Neissendorfer has shown that there's actually no torsion of other forms in the homotopy groups. So these are all the hyperbolicities that you could have hoped for. So the place my thesis occupies in all this is trying to provide some computable criteria for these properties. And computable here means homological. So suppose I have a space that I understand pretty well, call it A, and suppose I know that it's Z mod P to the R hyperbolic. And I want to transplant my understanding of A to an understanding of some other space X, right, via a map mu from A to X. What do I mean by that? Well, mu is going to induce a map on homotopy groups, and there's lots of torsion in the homotopy groups of A, and perhaps the map mu carries enough of this torsion across to X that I can conclude that X is Z mod P to the R hyperbolic. So can I produce criteria on mu under which this happens? Here's the simplest version of the theorem that goes like this. So I'm looking here at a suspension, sigma X, and the Moore space is playing the role of my special space A, and my prime can't be 2. But suppose I have a map mu like this, such that when I look on homology, ordinary homology with coefficients determined by the parameter I put into the Moore space, I see an injection. Well, then I get to conclude that the suspension is Z mod P to the R hyperbolic. So a couple of similar theorems exist. On the one hand, I can drop the suspension hypothesis, but having done so, I have to check this condition on loop homology rather than just on homology. And there's a similar result where, as my special space, instead of the Moore space, I take the wedge of 2 spheres. But the torsion in the wedge of 2 spheres is somehow better hidden than the order P to the R torsion in the Moore space. Somehow the P to the R torsion is built into the construction, right? The Moore space really wears it on its sleeve. But the wedge of 2 spheres, the torsion is better hidden. And so I have to use subtler detection methods. And in particular, one needs K-theory. Okay, here are some big questions that I really like to know the answer to. And maybe this first question is more of a scandal than a question. But apart from the circle, we don't know if any of the spheres are P hyperbolic for any particular prime. This would be a really good thing to know. And secondly, we actually don't have any negative answers whatsoever, right? So I've given you a bunch of examples and said, in these cases, these spaces do have torsion that grows exponentially. But we don't know any examples where we know that the torsion doesn't grow exponentially, but for a reason other than the trivial one, right? Which is to say that we don't also know that the space we were looking at was actually P locally contractible. And it would be super interesting to have an example of this form as well. So in the case of the sphere, lots of computations have been done, and one can make conjectures. So here I'm working at the prime 3. On the x-axis, I have the stem. On the y-axis, I'm counting the number of summands who are cyclic groups of order a power of 3, right? So this is the thing that you count when you look at 3 hyperbolicity. I've plotted a couple of lines here. Here are the 3 sphere and the 9 sphere, and also the equivalent question for the stable homotopy groups. And I'm using work of Toda and work of lots of people, which is tabulated in the paper More Stable Stems by Isaacson, Huang and Wu for the stable stuff. And so, one can look at these lines and try and fit some lines of best fit and guess what's going on. And that's quite fun to do. So, for example, for the equivalent 2 primary picture, right, I was working at the prime 3. Isaacson, Huang and Wu conjecture that the blue stable line ought to grow like a quadratic. But who knows at other primes what's going on. Okay, so what am I thinking about at the moment? With Reiji Huang, I'm thinking about the quantitative aspects of this picture. So what can be said more numerically, not just hyperbolicity, but how fast things grow, and what are the other characteristics of the manner of the growth. With Steve Amelot, I'm looking at the interaction between the homological criteria I mentioned above and the Cohen-Moore-Neisendorfer higher torsion in Moore spaces. With Stephen Theriault, I'm studying a conjecture of Moore for a class of spaces known as 2 cones. And I'm also really interested in ways in which this stuff might connect to lots of powerful machinery from other bits of homotopy theory, right? So there are some Lie algebra models due to Geiss-Hoytz, which describe unstable homotopy theory, and in particular the torsion. And also Goodwillie calculus might have something to say about these kinds of problems. I'm super interested in exploring this. So yeah, thanks very much for your time. Please feel free to get in touch. I'll be there at the second session in the networking event.